In this video, we can discuss the how the scattering angles are connecting in lab and center of mass frame. So, as earlier we have discussed that uh, lab frame and center of mass frame. So, in the that we have considered that this is the incident particle m1, which moves with velocity, having velocity v1l, and this particle v m2 at rest in the lab frame, and after scattering it will scatter through this angle theta 1, and having velocity this particle m1 has v prime 1 v1l, and here it is scattered through this target particle, it's scattered through angle theta 2, velocity is v2 prime v2l prime, and we can resolve the velocity component along x-axis y-axis in terms. This is cos theta 1, and this component is v1 and dash sine theta 1. So this is the scattering we have discussed in the lab frame, and this is before collision and this is after collision. Similarly, we have discussed before collision and after collision in the center of mass frame. So in the center of mass, we have considered that the particle m1 and m2, they are moving with velocity v1 c and v2 c in the opposite direction, and after in the this is before collision, and after collision they will scatter through angle theta, and this target particle scatter through pi minus theta. So this is, and we have also consider here the position of this particle m1. We can replace represent it with the r1l, and the in the center of mass the position of particle is this incident particle, we can denote it with the r1c, and the position of center of mass with respect to the lab frame, um, we can denote it with this r. So this we have already know about the position as well as what are their respective velocities and what are their components. So now we will hear now connecting the scattering angles in the lab as well as in the lab and center of mass frames. So in order to drive these expression, that in order to connect the scattering angles in lab and center of mass frame, we will write the expression for the what is this is r l. This is we are writing the position vector of incident particle. We can write this in term of this is position vector of particle m1 particle in center of mass frame, plus this is the position vector of center of mass with respect to the center lab frame. So if we differentiate it, that dr l1 dt is equal to dr 1c dt plus dry dt. So this is representing the velocity component, this is represent the velocity in the center of mass frame, this is represent the velocity of the center of mass. Or we can write this in this fashion, v1l is equal to v1c plus vcm this. And similarly for we can write the position vector of particle m1 after the collision, and that is in a similar fashion I can write this r prime 1l is equal to r prime 1c plus r, and this is on differentiating in similar fashion we can get this type of expression of the velocity of this is the after collision for particle in the lab frame m1 particle incident particle, and here this is the velocity of the incident particle in the center of mass frame, and this is the velocity of center of mass after the center of mass with respect to the lab frame. And you know that we have written here the what are the x component and y component of the after collision, so that we can write that what the this is v1 v1 prime 1l cos theta 1 x component is equal to v1 uh, C cos theta, this is cos theta, V1C prime cos of theta plus VCM along the x-axis. Similarly, the y component we can write this is V1L sin theta 1 is equal to V1C cos theta for this particle. This is V1C prime sin theta. So we wrote the x and y component of velocities for the scattered particle, and this we have for the scattered incident scattered particle, or you can see that after the collision we can write these components, and from this we can get this V1L. And now this is a, if we divide this equation by this, we can get here tan theta. These terms will get cancelled and we get this type of expression. So in this expression we get sin theta, and so this is connecting this theta 1 in the left frame, and this is angle is in the center of mass frame. So now in this expression we have to find the value of this VCM divided by V1C prime. We have to determine this component, and by evaluating this, getting the expression for this, we substitute here, and from this we can get the connecting formula, which is our objective here for connecting the scattering angle. So here our objective is now to find this parameter. So here in the left frame, before the collision, we can write the expression for the momentum, that is the m1 particle, and this is for momentum for m2 particle, this is for the center of mass. So by rearranging this, we can write the expression for the velocity. We can get the velocity of the center of mass, and in term of velocity of particle in the left frame. So we will get this type of expression by rearranging this. Similarly, so this is, we got this expression VCM, and earlier what we have know that this we have V1, see, we got this type of the relation here. We will substitute the value of VCM in this relation. So if we know this V1L, see, V1C, we will substitute the value of V's center of mass velocity here. By substituting this, on rearranging it, we can get the expression for V1C is equal to M2 V1L M1 plus M2. We will get this expression of the velocity of the M1 particle in the center of mass. And we will consider that the center of mass is at rest in the center of mass frame. If it is in the rest, then the total momentum before the collision and after the collision we can take separately this momentum before the collision is 0, and after the collision we can consider that equal to 0. So if we write this before momentum, that m1 in center of mass frame, this is m1 v1c, because here the velocity, they are moving in the opposite direction. So we will write here this is in opposite direction. So we will write m1 v1c minus m2 v2c. This momentum is equals to 0, and here the momentum along the x direction, we can write this is m1 v1c cos theta minus m2 v2 here this is momentum in this direction. You can write this is m2 v2 cos theta with a negative sign. So this is, we can write this again 0. So on rearranging this, from this we can get the expression for P2C. If we rearrange this, we will get the expression for P2C is equal to m1 divided by m2 v1c, and from this cos theta will get cancelled, and we get v2c prime is equal to m1 by m2. Here is both comes out to be same. Only difference is here is v2 v2c and here v2 prime and here v1c prime. So we get these type of expression by considering that in the center of mass is at rest in the center of mass frame. So before and after the collision we can separately take the momentum. Total momentum is to be 0. So from here be able to get the these type of expression. Now what we will consider that, for example, if we consider that collision is elastic, then what will happen in the center of mass frame? So you know that in center of mass that the kinetic energy should be conserved. If it is conserved, and here we can say that the speed of the particle is same before and after the collision. We have to because if the collision is elastic, then kinetic energy must be conserved, and velocity or the speed of the particle must be same before and after the collision. For example, here we write the kinetic energy that before the collision is half m1 v1c. This is kinetic energy of the particle m1, and this is kinetic energy for the m2 before the collision. And similarly, this is the kinetic energy after the collision for particle 1 and particle 2 in the center of mass frame. And we have earlier we have got the what is the value of, we have this from the center of mass we have evaluated the expression for the b2c and b2c prime. So here we can substitute the value of this b2c and b2c prime, value of these from these two expressions. If we substitute here, we can, if we substitute here, from here on substituting this we get these values. v1c comes out to be equal to v1c prime, and b2c comes out to be b2 dash 2c prime. So this is reflecting that on substituting these expression in this expression, which yield that velocity of the particle m1 before and after the collision is same, and velocity of target particle before and after collision in the center of mass frame is same, and that is representing that collision if when the condition is, this is true for when the condition is when process is elastic process, you can say, or elastic collision takes place. So now we can say that for the elastic collision the velocity they are same. And earlier we have derived the expression for the this v1c. So this earlier we have on substituting the value of vcm here, we can get the value of v1c is equal to m2 by m1 plus m2 v1. So here it means that this is the value of v1c, and I have written this is value of v1c, velocity of the m1 particle in the center of mass frame. So from for the elastic collision, this is for the elastic collisions, I can equate that v1c must be equal to v1c prime. They are same. And we know that the velocity of center of mass we have evaluated earlier, and that is this vcm is equal to m1 v 1c 1l m1 plus m2. This is the value. So this I am value here I have written, use this value vcm is equal to this. So this is earlier we know this expression, and if I now if I divide this expression by this, that vcm divided by v1c, so here m1 plus m2 will get cancelled and we'll get have to be m1 but divided by m2. And you know that for the elastic collision, v1c is approximately equal to v1c prime. So we can, this is uh, uh, evaluated, and you know that earlier our objective was uh, and we drive that our objective was this VCM divided by V1C here. So now we have evaluated this quantity here. Now we can, and this quantity is equal to m1 divided m2. So here in the earlier expressions, tan theta 1 is equal to sin theta divided by cos theta plus this quantity. We can replace this quantity with m1 divided by m2. So I'm substituting here in this, here I will replace this term with m1 by m2, and here you know that my trigonometry relation tangent square theta is equal to secant square theta minus 1. So this is the expression here. So I write this in term of cos theta, and on rearranging this we know this, we got this expression here, which is in term of 1 plus tan theta. This is simply we use the trigonometry relation, nothing else. And you know, we know that what is the value of tan theta 1, and I substitute the value of tan theta 1 here. On substituting here, I will get this type of expression here, which is cos theta plus m1 divided by m2, 1 plus m1 square plus m2 square plus 2 m1 divided by m2 cos theta. I hope that you can solve, you can uh, simplify. You will get this expression by simply substituting tangent value of the tangent theta here, and this is simply, you can get this type of expression. So this is the connecting formula. You can say this is connecting angle theta with theta 1 with theta. Theta 1 is the angle of scattering in left frame with the scattering angle in center of mass frame. This is theta. So so this is the expression. We have uh, able to drive this connecting relation for the particle. This is for target incident particle m1 in the both frame of reference scattering angle. Okay, so similarly for the this is for the target theta 2, for this is scattered through theta 2, and this is angle is in the left frame, and this is angle in the center of mass frame. So we seem in the similar fashion you can follow the same process, and finally you will get the angle. This tan theta 2 is equal to cos theta by 2, and we get this is the relation theta 2 is equal to pi minus theta divided by 2. So this is the connecting, this is connecting angle between theta 2 for the target in the center of in the left frame, and this is angle in the center of mass frame. So here this is scattering angle for the target particle. We can connect through this formula. So this is all about the connecting formula for the incident particle, bombarded particle, as well as for the target. So in this manner you can solve it.